Welcome to linear regression, modeling the relationship between two quantitative variables. So oftentimes when we view a scatter plot made up of real, actual bivariate data from a sample of individuals, one thought that might come to mind is, can I model the trend? I see a relationship. Can I maybe model that trend with some type of function? Well, and what does a model do? Well, a model models, right? It's not perfect. It's not exact. It's just used to help us make rough approximations or rough predictions. So here's an example. Here's a scatter plot showing the temperature versus sales of ice cream. So we see the temperature is the explanatory variable and the sales of ice cream is the response variable. The relationship looks positive, linear, and very strong. So as the temperature goes up, the sales of ice cream goes up as well. So any one particular dot is a day, and we noted the temperature on that day and the sales of ice cream that day. And it clearly looks like if it's hotter outside, we're going to sell more ice cream. Makes sense. But now, again, maybe we're wondering, okay, can I model this relationship? I definitely see it's linear, so it would make complete sense. If it wasn't linear, doing this would not make any sense. But since it does look linear, it makes sense that I would maybe use a line to model this relationship. And that's exactly what we're doing. So what is a linear regression model? It's a line of best fit. You've been calling it a line of best fit maybe back in middle school, but that's more of a middle school term. In upper level statistics, it's called the linear regression model. It's an equation that uses an explanatory variable, x, to predict a response variable, y. Now, the only difference, and this might not make sense now, but it will a little bit later, unlike in algebra, a linear model can take an x value and predict a y value. It cannot go the other way around. You cannot start with the y value and solve for an x value. Now go back to algebra class. Maybe you were given this equation and you could plug in x and get y, or you could plug in y and solve for x. We can only use these equations I'm about to teach you today in one direction. Plug in x, get y. Let's talk a little bit more about it. So here is the generic, extremely generic linear regression model. Now, the first thing I want you to notice is linear. Linear is a polynomial of degree 1. So we do see that we have a degree of 1 on my variable x. This definitely is linear. But it looks a little bit different than linear equations that you maybe have seen in algebra. So let's talk about a couple of the differences. First, what the heck is this thing on top of y? Well, it's actually called y hat. And it literally is like putting a little teeny hat on top of y. Now, that's super important that we have that there because that hat emphasizes that this is a predicted y. Models are used to make predictions. They're not made to be perfect, or they're certainly not made to be actual. They're just used to make predictions. I'm going to emphasize it a lot in the next couple of minutes of this video. So again, we put that y on there to say, hey, this is not a real y value. The dots in the scatter plot represent real y values. This is just a predicted y value. Then we have a plus bx, and you might be like, well, wait a minute. I'm used to y equals mx plus b. That's what I'm used to. Why are you changing everything around here? First off, you have a first, no m, and then you got a b. Where'd the m go, and why is the x in the back? Because this is algebra class. We don't use that anymore. In this statistics class, we use this equation. Now, it's still linear. We're just moving things around a little bit. Sorry, deal with it. So we actually start with the y-intercept first, and we call that y-intercept A. A is the y-intercept. In an actual problem, it will be an actual number. Then we have B. That is the slope. I'm sorry that we're not calling it M, and I'm sorry if that's confusing, but this is not algebra class anymore, it's stats class. So B is the slope of our model. Again, in an actual problem, it will be a number. And then we have X. So X is the explanatory variable. X goes in, multiply by the slope, add in the y-intercept, and you will get a predicted y. This is how we like to write these linear models for statistics class, so just get used to it. But again, in an actual problem, A and B will be numbers. X is the explanatory variable. That could change, 10 degrees, 30 degrees, 14 degrees, whatever you want it to be. And then out comes a predicted value. In our example, sales of ice cream. So let's actually see the model for our problem. So once again, here's that scatter plot of temperature versus ice cream sales. And I actually put the line of best fit in the model. There it is. Again, we don't really call it the line of best fit in this class. We call it the linear regression model, but that's it. There it is. It's a linear regression model. Again, it's a line that goes through your data, but I can't emphasize enough. If your data had a curve in it, please don't use a line. Everything in this video is pointless if your data has a curve into it. So the very first thing you should always do is make sure that it's even appropriate to be using a line, a linear model, and you simply look at the scatter plot and say, yeah, I guess it looks somewhat like a line. It's never going to be perfect. So again, in this scatter plot, the blue dots represent points, actual points. So for example, this point right here would have been actual day, but it was slightly over 14 degrees Celsius, and we earned a little bit over $200 in sales. So that's an actual X value, maybe 14.2 degrees, and an actual sales of ice cream, maybe $220 in ice cream. That's actual. But notice the red line makes predictions. The red line is right here. It's higher than what actually occurred. That is why when we use the linear model, it's so important that we put a hat on that Y, because the actual sales on this day were $220, but the model would predict something, looks like something a little bit more, maybe around $280. The point is, we have to really separate what's actual from the points versus what the model predicts from the line. That's why we need that hat on top of that Y. Super important. So here is that model for this class, or for this data, excuse me. Now, in future videos, I'm going to explain where the heck I got these numbers from. But right now, it's called trust. Just trust me. Right now, I'm just teaching you what the linear model is about and how to use it. So the linear model is Y hat equals negative 100.22 plus 27.51 times X. Now, what is Y hat? Once again, it's predicted Y values. These are predicted sales. Some kids will actually, instead of writing Y, they'll write the word sales and put a hat on top of that to really emphasize their predicted sales of ice cream, like really kind of making the equation in context for your problem. Negative 100.22 plus 27.51 times X, but X is temperature, so maybe put a T for temperature there. You don't even have to use an X if you want to use something that's more, in context to your problem. But again, this is simply the equation of that red line. You plug in T, a temperature, out comes a predicted sales. I can't emphasize for the second time enough, you cannot work this the other way around. You cannot take an actual number of sales of dollars of ice cream and backwards solve for temperature. Algebraically you can, but not statistically, because remember, this is not an actual sales of ice cream, it's a predicted sales of ice cream. So you cannot plug an actual number in there and solve backwards. Please don't ever do that. Big no-no. All right. So let's actually use it. Let's show how it's used. So once again, here is that equation, and maybe we say, hey, predict the price of ice cream sales at a temperature of 21 degrees Celsius. Okay, well, this is easy. So the predicted sales of ice cream, Y hat, is negative 100.22. Always show your work, even when it's easy. Come on. Plus 27.51 times 21. If you're really good at math, I guess you could do that in your head, but you'd have to be a genius to do that in your head. So typing into the calculator if you need to. Please confirm I'm right, but I'm pretty sure I'm right. $477.49. That again is predicted. Does that, and that's what I want to emphasize. Does that mean if it is actually 21 degrees today, are we guaranteed, lock, tight, solid, guaranteed, can't say it enough, guaranteed to sell $477.49 of ice cream? No, it's just a prediction. So go back to the graph. Again, that was my prediction point. 21 degrees would be right about here. And notice we predicted right around $480, like $477 in sales of ice cream. But again, that's just a model. The model's just making predictions. That's not a guarantee at all. So that's why we really want to put that hat on there. We can't emphasize enough that it's a prediction. Okay. Now, once again, do not go backwards. If someone tries to say, hey, on last Tuesday, we sold $510 worth of ice cream. Can we work backwards and solve for the temperature that it was on that day? And the answer is no, you cannot do that. Because remember, this spot right here is reserved not for actual sales of ice cream, but for predictions. So you cannot work backwards. Please don't think otherwise. Now, one more huge important thing to say here is extrapolation. What's extrapolation? Let me tell you. Definition first, and we'll go back and show you. Extrapolation is predicting a response value using a value for the explanatory variable that is beyond the interval of x values used to determine the regression line. Hold on, what? Okay, well, that's the formal definition, but let's go back and show you this. Our data ranged from 12 degrees to just under 26 degrees. So that means our model is only good at making predictions inside of 12 to 26 degrees. That's called interpolation. Interpolation is making predictions inside of the range of your data. My data range from 12 to 26, so it's only good at making predictions in that range. Extrapolation would be saying, hey, when it was 5 degrees, literally off the chart, 5 degrees, what would we predict? Well, listen, I could plug 5 degrees in for temperature and I could get a predicted sales, but it would be worth nothing because that's extrapolation. I'm reaching outside of my data. Interpolation is only looking inside of your data. Another example could be somebody says, hey, boy, it's going to be really hot tomorrow, 34 degrees. What is the sales of ice cream for 34 degrees predicted? I should not do it. Listen, can I do it? Yeah, I could plug 34 in for temperature. I could get a predicted sales. But would I recommend doing that? Absolutely not, because of extrapolation. Again, extrapolation is reaching outside of your data range. My data range from 12 to 26. So that means my line is only good at making predictions from 12 to 26. It would be bad at making predictions lower than 12 or higher than 26. You could do it, but not recommended. Probably not going to be very trustworthy. All right, that's it for this video. I think it's super important. The only last thing I'm going to make sure I say here is, remember, don't use a linear model unless your data looks linear. So a lot of kids will base their opinion based solely on correlation. But remember, a correlation of 1 or -1 does not necessarily mean a linear model is appropriate. Even curved data might have a high correlation, but you don't want to use it because correlation is only for linear data. So the only point here is, remember, this whole video is about linear models. So if your data doesn't look like a line, don't use a linear model. Okay, that's it for this video. You could shut it off, but I am going to keep talking. I'm going to do another example. So if you simply want to see another example, keep watching. Otherwise, feel free to shut it off. I would love you to keep watching, but you don't have to. All right, here's another example where we looked at the miles of the mileage on several different Ford F-150 Super Crew trucks and the price of those cars. So basically we looked at a bunch of used trucks. We look at how many miles were on those used trucks and how much those trucks are currently selling for. If we look at the scatter plot, it doesn't look like a great line, but I don't see a curve forming. I definitely see some type of roughly linear model coming through here. The data looks to be negative, somewhat strong, and pretty linear. It's not perfect, but it's not a straight curve, right? And the data shows that the more miles that are on a truck, the lower it's going to sell for. I mean, come on, that's common sense. If a car has a lot of miles on it, it's going to cost less money. And the model certainly shows that. So here is the actual model for this data. What I do, I put a line through the data. You guys have called it a line of best fit. I'm just calling it a regression model. And it's linear. So here is the equation. The predicted price, I use the actual price with a little hat on top of it. Y-intercept, 38,257 minus 0.1629, that'd be my slope, times x. You could use a generic x, but I like to actually use an m for miles, or you could literally use a phrase like miles driven here. But again, this is my linear model. That's the line. That's the linear model, right? I mean, it's so simple. Now, you might be saying, where did this equation come from? Stay tuned for more videos in the future that will definitely walk you through where I got these numbers from. But let's just use it. Like, it's so unbelievably easy to use. So predict the price for truck with 100,000 miles on it. So once again, look at the data. The data predicted this. Now, I don't want to extrapolate. I do not want to extrapolate. So is $100,000 a smart thing to do? Yes, $100,000 is right here. Oh my gosh, I'm so sorry. 100,000 miles, 100,000 miles. And that's inside of my data. My data looks like it was from maybe around $200,000 up to maybe 113, excuse me. Wow. I'm really off on my miles here. My data range, this is not dollars, this is miles. I'm getting confused on my own here. Okay, so again, it ranged from maybe 20,000 miles to as high as 130,000 miles. But the point I'm trying to make is this is interpolation. 100,000 miles is definitely inside of my data. So all I'm going to do here is I'm going to take my Y hat, my predicted price, 38,257 minus 0.1629 times 100,000. Grab a calculator. Definitely don't want to do that by hand. 38,257 minus 0.1629. Yes, I am using my calculator right now live in front of you because I don't want to mess this up. And I get a predicted price of $21,967. Does that mean if you go out and look for an F-150 Super Crew right now and it has 100,000 miles on it, I'm guaranteeing the price to be $21,967? Heck no. It's just a prediction, which is why this Y hat is so important. Once again, do not go backwards. You cannot take an actual price and work backwards for the mileage on it. It's just not how it works. It's not an actual Y, it's a predicted Y. And please, once again, do not extrapolate. My data ranged from, again, about 20,000 miles to as high as 130,000 miles, again, roughly in that frame. So trying to make a prediction for a truck with 400,000 miles on it would be stupid. Trying to make a prediction for a truck with 10 miles on it would be stupid. That's outside of my data range. That's called extrapolation. We don't want to do that. All right, that's it for this video. Hopefully you enjoyed it. Hopefully you now know how simple a linear regression model is.